Hello everyone and welcome to my YouTube channel. So in my previous videos we had a look at some example of supervised machine learning algorithms, and so for this video we'll be focusing our attention on an example of a supervised machine learning algorithm, which is the linear regression. So to make the best out of this video, I presume that you have some basic algebra understanding, then some basic calculus as well. So to start going, we're going to take a very simple example of height and weight of some individuals. So we have the height in inches and then the weight in pounds. So the interest here is that we want to come up with a model such that when we are given the height of any other individual we don't know in the future, we should be able to tell the person's corresponding weight in pounds. So first of all, let's plot this information on a graph and see how it looks like. So this is the height on the x-axis with the weight on the y-axis. So we see the plots of these and we can observe some sort of linear relationship in this. So in this case, the independent variable here is our height, which is the x, and then the dependent variable is our height, which will represent as y. The objective of a linear regression is to determine the extent to which there is a linear relationship between the dependent variable and one or more independent variables. So this brings us to understand what then are the types of linear regressions. We have the simple linear regression, which involves just a single independent variable being used to predict the dependent variable. So in the case of our example of the height and weight, it is a simple linear regression because we have just a single independent variable, that is the height, and a single dependent variable, which is the weight. Then we have example of a different type of linear regression, which is the multiple linear regression, which involves two or more independent variables used to predict the dependent variable. The task of a linear regression is to be able to predict the value of the dependent variable based on an independent variable. Basically, we are interested in finding the best fit line. This best fit line is just the equation of a line, which is given as yi is equal to theta xi plus epsilon I, right? These theta are parameters, and these parameters we don't know. It is also the slope of the line, and it's these values of this theta that would also help us get the very good best fit line. The x refers to the input variables. So with our example, the height would be this our x. Then this epsilon would hear or get to understand more about it in my subsequent slides. So we can have a best fit line as shown in this graph. The interest here is that this line is what we have been able to model and come up with. Then these are the actual values. We are interested in finding a line that would fairly create that the distance between the actual values that we have plotted and the line would be very small. That is the kind of line we want to have. And in that regard, we would come up with the loss function, which is the mean squared error. These yi's are the actual values, and then the theta xi's are our predicted. So we expect that the difference between these should be as small as possible. This is an example of the loss function of a linear regression. Note that there are other loss functions of a linear regression, but this is just one, which is the mean squared error. We would want to focus on how we can derive this mean squared error function. How did we arrive at this? So we can do this using the maximum likelihood estimation. Now for our equation of the line, which we had already seen, we had this epsilon. Now this epsilon we are going to assume follows a normal distribution with mean of 0 and standard deviation sigma squared. Now we can make this EI the subject, and once we make this the subject, we just take this our predicted y to the other side, then we have equation 2 as indicated. Now we want to find the probabilities of this, and since this follows a normal distribution, the probability density function of the normal distribution is given as this, as we can see in equation 4. So in this probability density function of a normal equation, the x will refer to our value that we have of EI, then the mu already we know it's equal to 0. So we just replace these values in equation 4, then we can have our equation 5 as shown in here. But note that these probability function, the probabilities of this EI are independent and identically distributed, which means that this we have here is just for one example, and if we want to look at it in the general case, we would have to take the product of it since they are IID, and so we can apply the product to this. So this is just a symbol of what we use in math as the product. So if we take the product of all the probability density function as we have here, so we note that we can apply the product through this function. Now we would want to maximize this function because we are using the maximum likelihood estimation. So once we have this, we want to be able to maximize this. How do we maximize this? This is an increasing function, and for any increasing function, we can maximize that function just by taking the log of that function, because the log is an increasing function as well. So the maximum of a function is the same as taking a maximum of an increasing function is the same as taking the log of that function. So once we take the log of this function, then so I apply the log in here, then we can have the rule of this, that an exponential of a times exponential of b is equal to the exponential of a plus b. So we can apply the product to this term only here, which is a constant, and apply the product to the whole of this term. But we can look at the whole of this term to give us a summation, because I'm using the rule here that this raised to the power a times this is equal to a plus b. So if you apply the product here, then this would become a summation. Now the next rule I would want us to use is the log of a times b is equal to log of a plus log of b. So now we can multiply the log through this system. So we're going to have the log of only that and then the log of only this, which is the same as expressing it as a sum. So we apply this here, then we have the log of that plus log of all of this. The other rule is the log of exponential raised to the power of a function is equal to that function, and the log of a raised to the power n is equal to n log of a. So applying that to this function we had here, this is going to become n log of all of this, and then this log of e will just become the summation of all of this, as we have in equation 11. Now we are interested in theta, because theta, like I mentioned, are the parameters that we want to find. We don't have theta on this side, so we can actually do away with this since theta is not here and focus our attention on this side of it. So how do we find theta? We can find theta by using the argmax. We use the argmax because we are interested to know the parameters that actually maximize this particular function. So we take the argmax of this. So when we take the argmax of this, like we have in here, then we would use the rule that the argmax of any function is equal to the argmax of any constant times the function for any constant which belongs to r plus. So if this is already 2 sigma squared, we can multiply this by the sigma squared. We can multiply this whole function by the sigma squared using this particular rule. So when we multiply this by the sigma squared, we can cancel the sigma squared and the sigma squared that would multiply, leaving this with the negative of 1 over 2 of all of this. But also, the maximum of a function is equal to taking the negative of the minimum of that function. So we can do away with this negative by minimizing the function. That's by taking the negative of this, since this is the maximum of it. So when we do this by taking the negative of this function, then we would get the mean squared error, which is equal to 1 over 2 summation from I equal to 1 to n of the actual values, that's y, minus theta times x, all raised to the power 2. So we would want to minimize this function. And once we minimize this function, we can do that numerically or analytically. Numerically, we can do with gradient descent. And for my next video, I would want to focus on how we can minimize this function analytically and then numerically. So we'll look at that in the next video. But with the increasing numbers of coronavirus, I would want to leave you with the words that you should please stay at home, remember to wash your hands, and keep distance. Adhere to all the rules of the World Health Organization, and together let us stay alive. And of course, if you enjoyed my video, please don't forget to leave a comment below, subscribe, and like this video. And I'll see you in my subsequent videos. It was a pleasure. Bye bye.